Okay, let us keep going. This is our recording number 3, I believe. Today what I want to do in this relatively short recording is talk about how an electron actually responds to an electromagnetic field that is passing through it. We talked about this a little bit, and so what we'll do is make this more quantitative, just so we can understand how the electron might move under the influence of the electromagnetic force that is due to the light wave. We're going to treat the light wave as a wave, so not as a photon, so not quantum mechanically, or we might say it's classical mechanically, i.e. in the realm of Newton's laws, and once again, not one of quantum mechanics. We're going to treat an electron as a point, which of course is ludicrous from a quantum mechanical point of view, but from a classical point of view, it's perfectly appropriate. We're going to treat the electron as a point that is going to be influenced by the electromagnetic wave that is flying by, effectively, or is filling the space where the electron is, moving both in space and oscillating in time. And so that's what I want to take up. Let me remind you what the situation looks like if we were to plot the electric field of our wave. Let's say the wave is moving in the positive x direction. We drew plots that look like this, where this was the electric field, in this case vertical in the plane of the board, oscillating up and down as a function of both space and time. The space part is obvious when we draw it like this. At first the electric field is pointing up, then it's pointing down, that's pointing up. And then we also talked about the fact that if you were to look at this electric field as a function of time, this electromagnetic wave, it would be moving at the speed of light. So this might be some other instance, then some other instance, we will move further. Now there's a lot of dashed lines going on here. And so at a given point, for example here, at one point in time the electric field is 0. Then in the next point in time when the wave moves, the electric field might have reached, according to my picture, a maximum. And then in the next instance in time it's here. And so at any given point in time, the electric field is also oscillating. So not only is the electric field oscillating as a function of space, and by oscillating we mean going up and down, changing the direction of the force, but also at a given point in space as a function of time, the electric field is also oscillating. And so what we're going to do is we're going to imagine that our electron sits somewhere in here as the electric field sweeps by it. And we know, kind of qualitatively speaking, that the electric field ought to make the electron go up and down as the electric field is passing through it of the light wave. And so we want to now treat this quantitatively and ask the question, what determines the motion of the electron? For example, how much does it go up and down as the electric field sweeps it, and at what frequency? And so to do this, we're going to make the electromagnetic wave a bit more quantitative, and we're going to say that the electromagnetic, first of all, let me make this clear. Our electromagnetic wave is sweeping forward in the positive x direction and oscillating in the plane of the board. Let's call the plane of the board the axis z, so that the y-axis might be coming out of the board. But so it's moving in the direction x, and it's oscillating up and down in the z direction. So for example, you could replace this by the z component of the electromagnetic field vector. And so this is the z component going up and down with respect to 0. So it's positive z at one point, negative z at another point. And of course, positive z means that a force is pointing upwards in the z direction. Negative z means it's pointing down in the z direction, so pushing things downwards. And so how might one describe this electromagnetic wave? We may say that the z component of the electromagnetic field as a function of time looks like some E naught, some constant that describes the maximum amplitude of the electromagnetic field, and a part that tells you how it changes in time. And I'm going to write it in a notation that may or may not be familiar with some of you. And before I write this, one thing we should know is that this wave is what's called sinusoidal, right? So it repeats like a sine wave. And when we say sinusoidal, we also include in that definition cosinusoidal. So as a cosine, the idea is that, of course, the sine and the cosine are offset from each other by 90 degrees, but otherwise functionally they look very similar, nearly identical. And so we're going to write this sinusoidal time dependence of the electromagnetic wave in what's called complex notation. And I know some of you might have encountered this, some of you might not have encountered this, but we're going to nevertheless write it down. We're going to write it as e to the power I omega t. I is the imaginary number, square root of -1. Omega is the angular frequency of the wave, and t is the time. Omega, let's write it over here. Omega is 2 pi times the frequency of the wave. So this is the frequency of the wave that we discussed last time in units of 1 per second. How many cycles per second? This is the angular frequency. Angular frequency, which is how many radians per second, right? So the only difference is that you take the frequency that is cycles per second, multiply it by the number of radians in a given cycle, 2 pi radians in a full cycle. And so the product of these two is the angular frequency, and it's oftentimes a more compact quantity to work with. So otherwise you can write this as I to the power of, or to e to the power of I times 2 pi nu, the frequency, times t, but we will write it as an angular frequency, 2 pi nu. What is this e to the I omega t? This is called complex notation for the sinusoidal time dependence of the wave. E to the I, let me write this. E to the I, let's call this some angle theta, has a very interesting form as written in terms of cosines and sines. This is called the Euler formula, and this equals cosine of theta plus I sine of theta. It's a really interesting proof that one can look up mathematically, but what this says is that I can take a functional form that looks like cosines and sines and write it in terms of a much more compact notation where it's an exponential raised to the power I theta. This we would call the real part of the wave. This we will call the imaginary part of the wave. And when we're speaking about physical phenomena, of course, we're referring to the real part of the wave. But generally, mathematically, it is much more convenient, and we don't make any error in writing this the cosinusoidal or sinusoidal form of the wave in terms of this exponential imaginary number notation. So e to the I theta, where theta is the angle of the cosine or the sine. And our angle here is the product of the angular frequency times the time. And so these guys together make an angle, which of course makes sense. If you take this quantity, which is 2 pi times something that looks like 1 over time, or 1 per second, times the time, the seconds will cancel, you'll be left with just the angle part, or in terms of radians. And so this is often called Euler's formula. Euler was one of the greatest mathematicians of all time, and many formulas are named after him, and many formulas sound like Euler's formula or the Euler relation or the Euler equation. This is called Euler's formula, and maybe some other people might call it Euler's equation, but nevertheless, this is what that is. And so with this notation in mind, we can now investigate how an electron moves under the direction of the electromagnetic wave. So how does anything move under the direction of a force? Remember that the electric field is related to the force. We haven't said exactly how, but we're about to say exactly how. We said that it is the force within a constant, and we'll see what that constant proportionality is. And so how does a mass point, an electron, a mass concentrated in a point, move under the direction of a force? What describes the motion of a mass particle or a mass point under the direction of a force? Whatever the force might be, whether it's gravity, whether it's electromagnetic force, and of course electromagnetic forces we've discussed before are felt by electromagnetic particles, or electric and magnetic particles, that are subject to electromagnetic fields. And so we imagine our electron is sitting somewhere here in space, and all of a sudden the electromagnetic wave sweeps through it. And we ask ourselves, how does this electron respond to the electric force due to the wave? And so to figure this out, we go back to the law that determines the way anything moves under the influence of a force in the Newtonian universe, under the laws of Newtonian motion. That law is, of course, the second law of Newton's second law, or sometimes just referred to as Newton's law, because it's by far the most important Newton's law. And what it says is that if you have a particle that has a mass, it will accelerate under the direction of a force. And of course, usually these guys are vectors. They have some magnitude and direction in space. We are only going to concern ourselves with the z direction, and so we might replace this vector equation and make this into an equation of vector components and write this acceleration in the z direction subject to the z component of the force, right, up and down. And this is going to be the mass of the electron. First, I want to discuss what is acceleration. Well, acceleration is the rate of change of the speed. So you might write this as d dt of the speed in the z direction. Of course, the acceleration vector is a derivative of the velocity vector, but the z component of the acceleration is the time derivative of the velocity component in the z direction, or the speed in the z direction. Well, what is the speed? The speed is, the speed is the rate of change of position. What is the rate of change of position? Well, let's call the position of the electron as a function of time z of t. So let's say d dt of z of t, where z of t is the time dependent position of the electron along the z-axis. So that's what z of t is. It is a function of time because the electron is going to be oscillating up and down. We already discussed this qualitatively. Because the electromagnetic wave, its electric field is oscillating up and down. So this is, the acceleration is the derivative of the position. And the derivative of the derivative is, of course, the second derivative. And so we may write m of the electron, second derivative of the position as a function of time, second derivative with time, equals the force in the z direction. What is the force of the electron in the z direction? This is where we come to our connection between the force and the electromagnetic field, or the electric field in this case. The force on the electron is the charge of the electron times the electric field. So that's the relationship. It is the charge of the electron, or the charge of anything, times the electric field in the z direction as a function of time. So that's the relationship. They are almost the same, except the force is the product of the magnitude of the charge times the electric field. And so the total force felt by a charge is the product of the electric field magnitude at a given point in time times the magnitude of the charge. So if this was a charge of, let's say, a helium nucleus, it would be a different charge than the charge of the electron, or the charge of the proton, which would be the opposite side charge of the electron. So at this point, we have not said what kind of charge, positive, negative, big, small, whatever it might be. We're just simply saying that the relationship between the force of this charge on this charged particle in the z direction is the product of the charge itself, the magnitude of the charge, times the electric field acting upon it. So very similar, but not identical. And of course, if one takes electromagnetism, much more time is spent talking about why the idea of the electric field is worthwhile introducing, given that it's almost the same as the force. What is the time-dependent electromagnetic force? Well, we said it here. It is equal to, first of all, we have, again, the charge times the maximum magnitude of the electromagnetic field. So the electromagnetic field, sorry, I should say the electric field at the peak of the wave, right? The peak, whether both up or down, and I guess peak in the absolute magnitude sense, times this constant E naught determines the maximum field times e to the I omega t. So now what used to be an abstract time-dependent function has now been made into an explicit time-dependent function. And if you wanted to, you could replace this, if you didn't feel comfortable, by cosine omega t plus I sine omega t per Euler's formula. And so now we have a differential equation that says the position of the electron as a function of time is determined by solving this equation that says the second derivative of the position as a function of time is equal at every point in time to this constant q times E naught, the maximum electric field magnitude, times this time-dependent function. And so this is called a second order ordinary differential equation. Ordinary because it involves only a single or a single variable with respect to which derivatives are taken. So here it's the derivative with respect to time. And what this says is that the solution of this equation, which will be the way the position of the electron changes with time, is found by finding that function of time whose second derivative multiplied by the mass gives rise to this function. And so there are techniques available to solving differential equations, and we're going to take a slightly different approach. It is often the case, as silly and funny as it sounds, that differential equations are solved by guessing their solution. And so we might ask ourselves, can we think of a function whose second derivative is going to be equal to some constant times this this time-dependent exponential, this e to the I omega t, this oscillating function. Remember, this is not any ordinary exponential. This is basically cosine omega t plus I sine omega t. So this represents a sinusoidal function. And last time we talked about the fact that as the electric field is oscillating up and down as it's sweeping through the electron will be set into oscillation and will also oscillate with the field up and down. This makes sense, right? As the field is pushing the electron up, the electron should want to go up. As the field reverses and pushes the electron down, the electron should want to go down, and so it also should oscillate in time. So we're going to do something quote-unquote radical. We're going to say, suppose we know what the solution of the electron of this differential equation is. And what we mean by solution of this differential equation, we mean the dependence, the position of the electron as a function of time along the z-axis. We're going to guess, literally guess, that the position of the electron as a function of time is also a function that looks like this, because of the physical grounds that we've just laid out, the physical reasoning. And so we're going to say, we're going to guess a solution, and we're going to see what the consequence of this guess is. We're going to guess that the position of the electron along the z-axis as a function of time is equal to some maximum position, some constant, also times e to the I omega t. That is to say, the time dependence of the electron position is going to be identical to the time dependence of the electric field. And let's check whether this equation satisfies, whether this solution satisfies the differential equation m, second derivative of position as a function of time, should equal charge on the electron E naught e to the I omega t. So how do we check whether the solution satisfies this differential equation? And also, if it does, what determines this maximum maximum extension along the z-axis? Remember that this function is a sum of cosines and sines, right? So the maximum value for this function is going to be 1. This quantity, this constant, determines what multiplies this function, how far does it actually travel along the z-axis. And so we're interested in this kind of a quantity as it relates to the variables of the problem. For example, the frequency of the electromagnetic wave, the charge on the electron, the maximum amplitude of the electromagnetic wave, and the mass. And so let's do this. The way we do this is, if we've guessed what the solution is, this tells us what to do. Take two derivatives with respect to time. And so let's do this. Let's take the first derivative, d dt of z naught e to the I omega t. That's the first derivative. First, this is a constant, so the derivative goes right through it. And so we have z naught d dt of e to the I omega t. What's the derivative of the exponential? It's the exponential function back, and by the chain rule times the derivative of the inside function. And so this is going to look like z naught, the exponential function back, times the derivative of the inside function. The derivative of the inside function is the inside function is I omega t, these are constants with respect to the derivative with respect to time, and so we bring down, in a sense, a factor of I omega when we take the derivative of I omega t. So that's the first derivative. Now we got to take the second derivative. So now d dt of the result of this business of I omega z naught e to the I omega t. We repeat this. Now these guys are constants, so the derivative goes right through them, operates on this e to the I omega t, and we get the same result back, right? So this looks like I omega z naught times the exponential function back times this business, I omega, and now let's put it all together. I squared omega squared z naught e to the I omega t. I squared is, since I is the square root of -1, this is -1 when you square it, right? So this is minus omega squared minus omega squared z naught, sorry, I don't know why I said omega naught, omega squared z naught e to the I omega t. And now we are effectively done, or almost done. Let's put it all together. Let's put all this together. Let's go back to here. What we found is that mass times minus omega, oops, this looks like, I don't know what that looks like. Omega squared z naught e to the I omega t equals the charge on the electron, for now we're keeping it as just Q, times E naught e to the I omega t. Of course, these guys are the same. We cancel them, and we solve, in this case, for the maximum displacement of the electron. What I mean by solve for that is we're saying we've solved this differential equation. We've shown that e to the, or that z naught e to the I omega t is the solution, or is a solution to that differential equation, if these guys, these constants, are equal to these constants, because e to the I omega t cancels on both sides. And so by having formed this equality, by having shown that this equality must be true for this to be the solution of this differential equation, i.e. Newton's second law, we are now in position to say, what does the maximum distance that the electron travels at its peak along the z-axis, how does that distance depend on the variables of the problem? For example, the charge, the maximum magnitude of the electric field at its peak of the wave, the frequency of the wave, and the mass. Let's solve for it. Z naught equals Q E naught divided by, or it's minus, m omega squared. Let's remember what Q now is. This was some generic charge, but now we're going to say that the charge on the electron is minus E. For the electron, Q, the charge, is minus E, where E is a positive number, the charge on the electron, one can look it up. Minus makes it explicit that it has a minus sign. And so if we do this, we find E, charge on the electron, the maximum amplitude of the electric field along the z-axis, divided by m omega squared. I'll write this as m omega squared. So in words, the maximum extension of the electron, both in the positive z and the negative z direction, the maximum distance it goes before it reverses its direction, is determined by the strength of the electric field. So the stronger the electric field, the larger the maximum of the electromagnetic wave, the larger the deflection of the electron up and down along the z-axis. The larger the mass, the smaller the deflection. And so per one of the questions that came up in the class, if this had not been the electron but the proton, the mass would be much larger, about 2,000 times larger. And so it would travel much smaller distance along the z-axis for the same electric field. And of course the frequency. That's really interesting. This says that the larger the frequency of the wave, remember the frequency is how fast in time the electromagnetic wave is oscillating, right? It's from this point. If the electromagnetic wave is oscillating very fast, the extension will be smaller. In fact, it will go as 1 over the square of the frequency. And so it is very sensitive to the frequency, and the larger the frequency, the smaller the distance along the z-axis that the electron travels at its maximum point, either up or down. Why might that be the case? The reason why that might be the case is that if the frequency is very fast, the electron at some point has trouble keeping up, and as it starts to go upwards, the electromagnetic field quickly reverses itself because of the higher frequency, and now the electron is pulled downwards. And if the frequency is very high of the electromagnetic wave, the electron barely has a chance to go up and down before the force is already reversed, sending it into the opposite direction. But if the frequency is very low, the electron can track the wave relatively well, and so as the wave goes up in force, the electron tracks it and also goes upwards. As the electric field reverses and goes down, the electron also feels it and reverses it, and is able to track it very well. And so the smaller the frequency, the farther along the z-axis the electron is able to accelerate before and therefore move before it is forced to go back down. But if the frequency is very fast, oscillating very quickly, the electron can scarcely go up and down, and so it's very able to go a little bit before the field forces it to go back. And so we found a quantitative way to describe the motion of this point particle electron, non-quantum mechanical, classical, or Newtonian electron, that is subject to the electromagnetic wave in a point in space. And of course, we are also imagining that the electron is kind of sitting in this position along the x-axis. All it could do is go up and down with the electromagnetic wave. And so we've now made this more quantitative. There's a spider on me that I would like to get off. But nevertheless, that's what I wanted to convey.